Hello everyone, Medic Level Up here, and I am back again with another video. Today we're going to be talking about acid and base disturbances. I get a lot of people on a day-to-day basis that tell me that they cannot adequately interpret the arterial blood gases, they cannot make sure which acid-base disturbance is going on, and today we're going to be tackling all of those. Okay, but before we do so, we're going to break this video down into 4 parts. Okay, so there are 4 primary disorders and we're going to discuss one disorder at a time. I have always noticed that if you go through all these 4 disorders at the same time, there is a lot of confusion and you don't retain anything. So the first thing we're going to be talking about is metabolic acidosis, how you detect it, what are the differentials, how do you detect a co-existent component, is there adequate respiratory compensation going on. All of those things are going to come in a while. Let's get started. So you're standing in the ED. There is a patient who comes in and he is acutely unwell. Your consultant decides to get in arterial blood gases and he hands you the sample and he says, "Doctor, I want you to interpret this sample." Now, what is the first thing you look at? It's the pH. Let's go over the normal values one more time. So the normal pH is 7.35 to 7.45. The normal PCO2 is 40 and the normal bicarb is 24. Okay, now there is obviously ranges, but the reason I'm using these numbers is the fact that we'll be using these numbers later in some formulas which are important. So the first thing you look at is the pH of the patient. Now let's say, for example, you have a patient whose pH is around 7.14 and the PCO2 is 23. Now there are a set of rules which we want to apply to this condition. Rule number 1, if you see that the patient's pH or the PCO2 or both are abnormal, there is an acid-base disturbance. We're going to take baby steps over here. So that's the rule number 1. Hold on to that. Okay. Now rule number 2. If you see that the pH or the PCO2 is abnormal, compare the directional change in both of these values. Now what does that mean? You want to see where the pH is going. Is it going up? Is it going down? Is the PCO2 going up or is it going down? Now here's the thing. If the PCO2 is going up and the pH is going up at the same time, they are moving in the same direction. When they move in the same direction, the primary disorder is a metabolic one. If they move downward in the same direction, it is again a metabolic disorder. Okay? Now in our example, the pH of the patient was 7.14. This was going down. At the same time, the PCO2 was also going down at 23 millimeter mercury. Now, we have established up until now that this is a primary metabolic disorder. The next step, the next rule, is to see whether in a metabolic disorder where the pH is going. If the pH is going down, it is basically a acidosis. If the pH is going up, it is alkalosis. This is pretty straightforward. Take that as rule number 3. You see the direction of the pH and you determine whether it is acidemia or alkalemia. Now putting these two things together, you have established that the directional change in both the PCO2 and the pH is going down, so it is a metabolic disorder, and that the pH is going down, so it is acidemia. So this is metabolic acidosis. Now what's the next step? Now the next step is going to be calculating the anion gap. Whenever you have a patient with metabolic acidosis, the second step is always going to be calculating the anion gap. The anion gap is basically the net positive charge minus the net negative charge inside the body. So let's take the extracellular ions. Okay, the extracellular ions are going to be sodium, chloride, and bicarbonate. Most people do not use potassium in this equation because potassium is primarily an intracellular ion, so we're not going to put that into the equation when we're calculating the anion gap. So when you calculate the anion gap, let's take a normal value of sodium, let's take the normal value of bicarb, let's take the normal value of chloride. You solve that equation and what you're going to get is a normal anion gap of 12. There is a range for this. It's 12 plus minus 4. So what you're looking at is basically 8 to 16 of a normal anion gap. Now what's going to happen is there are some conditions which are going to elevate the anion gap, which are going to keep the anion gap as it is, and which are going to decrease the anion gap. Let's talk about the most common of these disorders, which is a high anion gap metabolic acidosis. Okay, so high anion gap metabolic acidosis means that the anion gap is going to be more than 12, okay, which means that there is a net positive charge inside the body, which is created by the unmeasured positive ions. Okay. Now, there is no way around it. You have to memorize this mnemonic. I'm going to throw it on the screen over there. It is cat mud piles, carbon monoxide poisoning, toluene poisoning, methanol, uremia, diabetic ketoacidosis, alcoholic ketoacidosis, paraldehyde poisoning, isoniazid and iron poisoning, lactic acidosis, ethylene glycol poisoning, and salicylate poisoning. There is no way around it. You have to memorize this. Okay, so whenever you see a patient with positive anion gap, metabolic acidosis, you have to think of these diagnoses. Now, there are some conditions that are going to keep your anion gap as normal. The mnemonic for this is going to be fused cars. F is for pancreatic fistula, U is for ureteral enterostomy, S is for saline administration, which is done during resuscitation, E is for endocrine disorders such as hyperparathyroidism, D is for diarrhea, C is for carbonic anhydrase inhibitors, A is for ammonium chloride, R is for renal tubular acidosis, and S is for spironolactone. There is no way around this again, so you're going to have to remember this one as well. There are also some conditions that are going to keep your anion gap down or narrow. These conditions are known as narrow anion gap metabolic acidosis, and there's only a couple of those, which is lithium poisoning, polyclonal gammopathies, and multiple myeloma. There is two more things I want to discuss over here regarding the anion gap. Number one, in critically ill patients, there is usually hypoalbuminemia. Albumin is basically a negatively charged protein that is present in the plasma. So whenever there is hypoalbuminemia, you have to adjust the anion gap according to the albumin levels. There is a pretty easy equation, which is anion gap plus 2.5 multiplied by the change in albumin levels, and I'm going to throw it down on the screen. So whenever you calculate the anion gap and there is metabolic acidosis, take into account the hypoalbuminemia. The next thing is that there is a lot of people who are watching this video who know that there is usually a sodium correction which is done in the presence of hyperglycemia, and there is one condition which is diabetic ketoacidosis, in which the blood sugar is sky high and you need to do sodium correction. But when you are calculating the anion gap, there is no need to do sodium correction, because the same blood sugar, the same factors that are diluting the sodium are also diluting the negative ions, which is chloride. So there is no need for sodium correction in the presence of hyperglycemia when you are calculating the anion gap. Now, let's say you're done with the anion gap. What's the next step? The next step is basically calculating the respiratory compensation. We want to see whether the metabolic acidosis is being compensated by the respiratory system. To be using the Winter's formula for this respiratory compensation. Now, the first thing you want to do is, let's take an example. So you have an ABGs which says that the pH is 7.32, the PCO2 is 23, and the bicarb is 16. Now notice that the PCO2 is going down and the pH is going down. This is a unidirectional movement, so this is a metabolic disorder. In a metabolic disorder, as rule number 2 states, you have to look at the pH. If the pH is going down, it is acidosis. Now this is a metabolic acidosis scenario. Okay, so let's say that you have calculated the anion gap and you've put it aside for a while. Let's come to the next step, which is respiratory compensation in this specific example. I'm going to throw the Winter's formula up on the board, and you can see that it is delta PCO2 is equal to 1.2 multiplied by delta bicarb. At the start of the video, I told you guys there are going to be some normal values, which is 40 for PCO2 and 24 for bicarb. Let's throw these values into the equation, and from the example, we're going to take another value of the bicarb, which is 16. So the equation becomes something like this. Delta PCO2 is equal to 1.2 multiplied by 24 minus 16. So 1.2 multiplied by 8, and that comes down to 10, which is a rounded off value in order to make our life easier. So you have a value of 10. Now you throw it on the other hand side of the equation, so it becomes 40 minus 10, which is 30. So this value of 30 is basically the expected PCO2. We expect the PCO2 to be at this level. On the other hand side, in the example, we have a measured PCO2 of 23, which means that there is a secondary respiratory alkalosis going on at the same time with this disorder. So a primary metabolic acidosis along with a secondary respiratory alkalosis. I hope that was clear. In order to complicate things even more, there is one more step you need to do, which is the delta-delta ratio. So it is the delta anion gap and the delta bicarb ratio. So the normal value for the anion gap was 12. You put that into the equation, subtract the anion gap that you actually have from the patient, and then on the bottom side you also take the normal value of the bicarb, which is 24, and subtract the patient's bicarbonate from that. If the ratio comes down to be 1, it means that the metabolic acidosis is pure. If the ratio is less than 1, it means that there is a co-existent metabolic acidosis, which could be a normal anion gap metabolic acidosis. If the ratio comes out to be more than 2, it means that there is a co-existent metabolic alkalosis along with the primary metabolic acidosis. Okay, so an example is thrown onto the screen, which is going to be from the same patient that we studied, which had a pH of 7.32, a PCO2 of 23, and a bicarb of 16. Now let's review all this, because this was the toughest disorder and it has like a lot of steps. So let's make a summary of this. So number 1, what you do is you look at the pH, look at the PCO2, look at the directional change. If it's moving in the same direction, it's a metabolic disorder. If it is a metabolic disorder, you look at the pH. If the pH is high, it is alkalosis. If the pH is low, it is acidosis. In our case, metabolic acidosis. The next step, calculate the anion gap. You need to remember all 3 mnemonics for the anion gaps: high anion gap, normal anion gap, and a narrow anion gap. There is no way around that. The third step is to calculate the respiratory compensation to see if there is a co-existent respiratory pathology. The fourth step is to calculate a delta-delta ratio, which is a delta anion gap and a delta bicarb. And there you have it. That's the entire summary of how to interpret arterial blood gases, especially when it is a metabolic acidosis. We're going to be doing the next 3 disorders one by one, because I don't want you guys to get confused. If you have questions, don't hesitate to drop them down in the comments below, and I will try to answer every other comment, or maybe message me on my page, on my Instagram, on my Facebook, and make sure you guys follow us. Thank you so much. Have a good day.